Hello, my name is Tom, and I'm going to be talking to you today about some work I completed recently doing housing inventory analysis. I leveraged a data science framework, and you can see that expressed here on the right. And this maps to our outline as follows. So we have a problem statement. This maps to the ask portion, the data gathering, where we get the data exploration, where we obviously do the data exploration, and we build the model, and then finally we provide the summary results. That's what we're going to talk about today. Go through the problem statement first. So here as I record this today, in December of 2021, housing inventory, or rather the shortage of it, is a major topic of discussion. Inflation is rather high, there's a lot of demand, remote working has rather exploded, and a lot of folks are looking for a change in lifestyle. And this has caused a shortage in housing inventory. But is there a way that we can look at a rather developed model to explain housing inventory as a function of several other inputs? And that's really what we're looking at here. And many factors go into the overall housing inventory rate. So there's mortgage rates, employment trends. I mentioned the remote versus in-person requirements previously, planned housing construction, so permits, the rate of federal funds, consumer debt ratios. And what would we do if we had all of this information, all this data across all of time? Well, we could probably build a pretty precise and accurate model. There's many things we could do. We could make a lot of money from a commercial sense. And on the public sense, we could probably come up with some really efficient policy decisions and come up with a lot of good things from a public perspective. So let's look at the data that was readily available to inform the ask with our subset of all available data. So what we looked at was, again, using housing inventory as a thing that we'd like to explain. Let's look at the building permits, the mortgage rates, the prime rates, and the revolving credit. And for that housing inventory, we looked at some historical data from Realtor.com. Building permits, these are things that are, it's not at a federal level, although the data source is federal. This is an aggregation of local authorities that issue building permits, both for new builds and for remodels. Mortgage rates, very common, many different flavors. This focused on the 30-year fixed, and the data source was Freddie Mac. And Freddie Mac is a provider in and of itself, but we leveraged the survey data that looks across a number of providers. Prime rate is a rate that the 25 or so large banks actually provide to their best or prime customers. And Federal Reserve provides this information. On the revolving credit, this is something that is recorded in the millions of dollars. So each unit is a million dollars, and it's across all folks across the United States. And once again, we leverage the Federal Reserve, that data source as well. And this is scoped just 2016 to 2020. Getting this data is really the ETL portion of it, and this is a summary of the process leveraged. Later on, we've got a reference to the actual GitHub repository with all of the technical details, so this data can be completely, or rather this analysis can be completely repeated. So one of the big challenges was time. We had a lot of variability across all the data sets. Some were provided monthly, some were provided weekly, others were provided in yearly increments. And there was a lot of different ranges. So we focused just on the 2016 to 2020 timeframe. And we built a composite key of month and year and use that to lock everything together across all the data sets. And then we actually dropped the time key when we were doing the actual analysis. This isn't a time series analysis. This is just an analysis to see if we could build a hypothetical model to explain what the overall housing inventory was. So I talked about that a little bit there in the time side, but on the general challenge, we had 5 different classes of data sources, 9 discrete files, 2 different file types across those. We had text and spreadsheet. Not everything lined up. We normalized to week year for each observation. There was some expansion, some contraction. We took and turned all of the textual data into Excel data just to normalize the import process. And then we put it into a SQLite database. You can see in the schema there to the right. And then at runtime, when we're actually doing the analysis, we use the common table enumeration with inner joins. And inner joins is a way to make sure that we've got cohesive data across, and essentially anything that's null on either side is left out. With these inner joins, we still had 18,000 observations, 18,000 plus observations. So let's get into the actual exploratory data analysis piece of it. So again, you can see there at the bottom, there's a footnote to look at the GitHub repo for the in-depth analysis. But summary information out of this single variable analysis is our housing inventory. We see that there was the vast majority were closer to, or rather under like 500 across all the CBSA codes. And CBSA codes, I'll get into that a little bit later. That is a normalization mechanism that allows for federal level reporting where we can identify metropolitan areas. And we had a lot. Majority of the instances were under 500. Then moving to the right a little bit, and again, this is a little bit of an eye chart. More information is available in the notebooks at the GitHub repo. Looking at the e-mortgage rate and the prime rate, a lot of folks would expect those to be exactly the same. And in fact, they have opposite trends. So that was one thing that was unexpected that came out in the single variable analysis. Lastly, I mentioned CBSA codes. There's a total of 935 currently registered, and the current paradigm goes back to 2014. In our housing inventory only data, there was 917 unique instances. And when we got down to the unique CBSA codes identified in our in that CTE query, we only had 398. And there's probably a few different reasons. We'll get into that a little bit area. We'll get into some of the root causes for that later. I mentioned we went with inner join. There's a strong possibility that those lower instances were actually omitted. So perhaps in future analysis, those could be included. Moving into the paired analysis, the interesting thing there on the left is the housing permits to housing inventory that actually had a fairly linear relationship. Although there is a fair amount of heteroscedasticity, there is a line that could be drawn through that that's fairly straight. Looking across the rates, we see a strong trend across the mortgage rate, the prime rate, and then the revolving credit. They all have very similar shapes and quite a bit of spread. So just interesting thing that came out there. Mentioned that there was 398 unique CBSA codes. Looking across the inventory, the 3 areas that had the highest inventory were in the New York, New Jersey metropolitan area, the Chicago, Naperville, Elgin, or Eglin, Wisconsin areas, and the Miami, Fort Lauderdale, West Palm Beach areas. Let's go into the actual data modeling now. So to start off, a causal loop diagram. Agree this isn't a diagram, this is just a table. Kind of thinking through things, we'd expect a kind of a positive relationship between the number of permits issued and the housing inventory. Similar on the mortgage rate. Credit on the other side, we think that would probably be negative because as more credit goes up, people have less money to apply to mortgages. And then on the prime rate, similar to mortgage rate, I think that would probably have a positive relationship. Looking at the actual mathematical correlations, we see that there is a strong indication of, on the housing permit side, just looking at the R correlation there, and it's 0.77, so that runs 0 to 1, so pretty strong evidence of the correlation there. And looking at Spearman's Rho, that's monotonically increasing. So that is well aligned to that CLD table above. So we start off with our null model for our data model. And that's just looking at the mean of the housing inventory there. And we see we've got a mean of 3,634 some odd houses with an error of 8,178 houses. Looking at our 95% error bounds across the mean, we see that's well into negative territory and then well into positive territory. Obviously, we can't have negative housing inventory, so we rebound this as 0 to 10,757 for our null model. Moving into actual modeling with our linear regression, we say let's just throw everything in there. So we go ahead and do a one-hot encoding of all 383 codes. We run the linear regression. We come up with a much better error value than our null model, and our R squared is really fantastic. It's very close to 1. It's a great model, but I mentioned there's 383 different coefficients that correspond to each CBSA code that's in the data. And that's just not usable at all, far too precise for general use. So let's see what happens if we modify this a little bit. Let's throw out all the codes and see what happens. And we see our error is 5,194, still better than our null model, so that's good. R squared is only 0.6, so not the greatest. We'd like to see something a lot closer to 1. Doing a check of our residuals, we look at our housing permits, and we see what looks like a lot of heteroscedasticity. So that might be something we should look to improve in future analysis. Let's go ahead for linear model 3 and add an interaction rate between the prime rate and mortgage rate. We mentioned before that was one of the things that folks expected to be strongly correlated, and they were actually inversed. Our error did improve slightly, but our R squared, not so much. So let's see if we can improve this a little bit more. Let's add some interaction rates across everything. So for all the mortgage rates and then the revolving credit rates, we see that expressed here. Our error improved a little bit more, but our R squared is still only 0.6. So mentioned heteroscedasticity and housing permits. Let's just try taking the natural log of those and see what happens. And with all of the other interaction rates. Well, that ended up not being the best thing to do. Our R squared went up significantly, still better than our null model, but our R squared dropped to 0.31, so that's not the way to go. Let's for this round of analysis, let's just go with linear model number 4. So this is the expression of linear model number 4. The prediction is expressed mathematically, and then the table results are shown below with the specific enumerations per coefficient with the mean, and then the 95% confidence interval for each of those. We then on the right see, let's go ahead and run a cross-validation through a few of these to get some better credible bounds. And we see that our error for this model runs 43, 49 through 6031 for the error, and our R squared is still 0.55 through 0.065. And it's like, why is this happening? And probably the best answer right now is the lack of capturing the CVSA codes correctly, essentially just abstracting across them instead of doing some additional work to regionalize those. So let's go into the summary results. We identified that things probably could be improved with future analysis, but let's do some predictions with our best model. And again, that best model was linear model number 4. So the first one, we're going with something reasonable, something well within the data bounds. 5,000 permits, mortgage rate of 2%, revolving credit of 750,000 millions of dollars, and a prime rate of 4%. Linear model predicts we're going to have 45,835 houses, reasonable error bounds. This is all intuitively reasonable. Prediction 2, let's go far beyond the range of our data. We've got 15,000 building permits, a mortgage rate of 10%, $1 billion of revolving credit, and a prime rate of 8%. Well, this linear model predicts that we're not going to have any houses there. That's what that negative 879,000 predicts. And there'd be no available houses in that scenario. So flipping the script a little bit for prediction number 3, let's go ahead and look at this with only one building permit and ideal mortgage rate of like a 0.5%, only $1 million in revolving credit, and a prime rate of 0. Thanks for just giving the money away to everybody there. Our linear model predicts 77,886 houses. We've got a reasonable error bounds. It's interesting from a theoretical perspective, but it's not pragmatic at all with only a single permit. That said, let's go ahead and seek to maximize what the theoretical maximum output of this would be if we bump up that housing permits in scenario 3 to 5,000. Let's see what our prediction looks like. We do that, we come up with 129,735 houses in the month for that theoretical area. Got a reasonable error bounds, and we can surmise that perhaps increasing the building permits would, in a favorable scenario, would increase the overall housing inventory. So if that could be influenced with policy or something like that. So to close out, our precise model was far too focused. General model was okay at best. Certainly there's things that could be looked at with regionalizing CVSA codes, perhaps reducing some of the heteroscedasticity that we saw in the building permits. So I encourage everyone to fork this analysis on GitHub and take it to the next level. Here's some references. These are also made in each of the notebooks. So thank you very much for your time. Take care.